In this lecture, we consider interstellar travel. We talked about communicating in the universe through electromagnetic radiation, and the fact that intelligent civilizations are likely to communicate in this way because of its efficiency and the speed of light and other forms of waves. But there's something vaguely unsatisfying about that passive mode of communication. We might imagine that it's our destiny eventually to leave the planet and travel through the galaxy. And we might imagine that a civilization with a head start on us, or one that's had more time to evolve, has achieved this capability too. So it's worthwhile considering what it would take for us, or for anyone, to travel through space, to actually colonize the galaxy, or move directly into realms where they can find kinship among the stars. The travel times in space are enormous. The Apollo 10 astronauts achieved the fastest speed humans have ever traveled, reaching close to 40,000 kilometers per hour on the return trip from the moon in 1969. It seems an impressive speed, but at that speed it would take over 100,000 years to reach Proxima b around the Proxima Centauri star system, which is the closest exoplanet that might be Earth-like to us. It's otherwise undoable. There's no way we can go fast enough. Because interstellar distances are so large, we can't go fast enough unless we go close to the speed of light. And that is physically not possible for large objects. The energetic requirements are too large. Using these same numbers, the fastest speed humans have ever traveled, it's hundreds of thousands or millions of years to reach most of the Earth-like planets we've found so far. The need for speed was realized early on in the space program. But there's a limit to what humans can withstand. The G-forces that some astronauts experienced in their launch and landing are tens, and 25 or 30 is enough to kill a human being. But aside from the limit of acceleration, there's a practical limitation of humans simply not living long enough at the slow speeds we can manage in the solar system. Partly it's an issue of propulsion. Spacecraft engineers have made significant advances, but it's even worth remembering that in the age of SpaceX and Blue Origins, and the private space industry about to send humans into routine Earth orbit, that rockets have not changed substantially from the Saturn V rocket that took astronauts to the moon. We're still using same old technology, actually very similar to used by Robert Goddard, so almost a century old. If propulsion technology is still using chemical energy, which is tens of millions of times less efficient, for example, than fusion energy, then we're going to be stuck in the solar system for a very long time. We can get slight boosts from gravity and by being clever, and in the space program by NASA, we've used gravitational assist, which essentially uses the gravitational energy and motion energy of fast-moving astronomical objects like planets and moons to boost the speed of a spacecraft. It's a clever trick that we've used to get space probes to the outer solar system relatively quickly, and to eject some objects from the solar system entirely. But it's not a routine way for us to leave the solar system and travel to the stars. Could we actually reach the speed of light? If you extrapolate and trust the extrapolation, if we achieved a roughly 17-fold improvement in our maximum velocity every half century or so, humans might eventually, in a few centuries, achieve speeds of a few percent of the speed of light that would make interstellar travel feasible in a few generations. But the implications of these calculations, the extreme energy cost of moving a large object like a rocket or a human being to anything close to the speed of light, or even 5% of it, is that a new technology is needed that we haven't talked about so far. It's the need to take humans into a state of suspended animation, bringing down their body functions to a tiny fraction of their normal level so that they can re-emerge after years or generations in a distant star system. Now, during that time, of course, they would still have to be protected from cosmic rays and damaging radiation, which would otherwise accumulate tissue and cell damage during the time they were frozen. And such technologies for suspended animation simply don't exist right now. In the medical profession, there are rudiments of suspended animation technologies that exist. The ability to replace blood with a body fluid that can be chilled. Remember, because water expands when it freezes, when a human is frozen, their cells explode. So you'd need to replace their body fluids with something like glycol. And then taking the brain and the metabolism down to a tiny fraction of a percent is a job that can't be done without destroying the brain. So at the moment, the obstacles to suspended animation, which is what would be required at the moment to send a starship to a distant star system, are beyond us. Is that going to be true in a century? We don't know. Meanwhile, there's been interesting progress at the small end. So if we set aside the idea of humans themselves traveling, we could send space probes, or emissaries. And remember, that may sound disappointing, but that's what we do all the time. We use technology as extensions of our capability. Spacecraft are already our eyes and ears, traveling to Mars and distant parts of the solar system or close to the sun. They're essentially extensions of our senses. And so we can use space probes in this way to explore large distances. Miniaturized space probes represent an interesting possibility. And the project announced a couple of years ago, Breakthrough Starshot, which involved luminaries like Stephen Hawking and others, is an initiative partly funded by the SETI Institute and Yuri Milner, Russian industrialist, to explore methods of achieving, if not near light speed travel, then at least 5 or 10% of the speed of light. So it's the idea of miniaturized probes. In the case of Breakthrough Starshot, the idea is to have probes that weigh perhaps a billionth of a gram, extremely small, and yet have sensors in that miniaturized package, attach them to solar sails, and then propel the probes by shining radiation from incredibly powerful lasers on the Earth's surface at the solar sails. In theory and in principle, such technology could accelerate those tiny probes, nanobots if you like, up to 5 or 10% of the speed of light. And at that speed, to go to Proxima Centauri would take 2 generations, 40 or 50 years. Breakthrough Starshot lists a series of several dozen technical challenges required to do this project on their website. None of them are impossible. None of the challenges involve breaking the laws of physics. But doing this project will take an enormous effort and far more than the money that has been committed so far. But the idea that we're perhaps within reach of sending emissaries, robotic emissaries, to a nearby star system that could contain an exo-Earth is incredibly exciting. And it brings to mind another idea from the 1950s, from a contemporary of Fermi. There's the idea of the von Neumann machine. Johnny von Neumann was a Princeton professor, founder of the field of computer science. Von Neumann was aware that the miniaturization of technology, even though computers in his day were the size of a family home, might lead to the point where probes could be robotic and miniaturized. He also realized that it was possible that such probes could land on asteroids or small rocky bodies and mine metals and materials to create replicas of themselves. The von Neumann machine is the idea of a miniaturized probe that passes through the solar system, mines rocky and metal materials to make replicas of itself, and then exponentially propagates through the galaxy, making more and more copies of itself which send back the information at light speed. If such technology existed in other hands, it would actually take only a 10 million year period to explore the entire galaxy with these sentient probes, beaming their information back to the home civilization. Has that ever happened in the history of the galaxy? Does the fact that we're within reach of that technology within maybe a century or so mean something about the existence of life in the universe? At this point, we don't know. The obstacle to us traveling in space, as opposed to just communicating electromagnetic radiation, is the difficulty of achieving high speed, and the fact that humans are large objects and the energy cost of getting to even 5 or 10% of the speed of light are prohibitive. So at the moment, we're stuck in the solar system. Without a new technology for suspended animation, so that humans could be taken to a wait state for a multi-generational trip to a nearby star, this isn't going to happen anytime soon. However, the technology of miniaturizing probes and accelerating them with solar sails and pulsed lasers to significant fractions of the speed of light is doable, and there's currently at least one project to try this. Either way, it seems likely within a century we will leave the planet forever.